Today, we are going to review a critical application in a petroleum refinery, the selection and specification of a centrifugal pump for the Crude Distillation Unit, or CDU. The plant receives the crude oil from storage tanks, and this pump, designated P101A or B, is the first step in moving that crude through the preheat train and dissolved before it enters the atmospheric distillation column. It is the heart of the operation. The pump we are studying is an API 610 OH2 type. This is a horizontal, single-stage overhang impeller pump, meaning the impeller is mounted on the end and the shaft is a centralized mount. The EOB designation indicates that we have two identical units, one for continuous duty and one as a standby for reliability. Let's look at the service conditions. This is a crude oil transfer pump operating on a continuous duty cycle. In every refinery around the world, this pump is truly the heartbeat of the CDU. If this pump fails for any reason, the entire unit shuts down, leading to significant production loss. This is why we have one pump online and another on standby, ready to start automatically or be swept in. The reliability of this pump is paramount, and that reliability starts with the correct hydraulic design and selection. Before we can do any calculations, we must define the fluid we are pumping. Here we are handling Arabian Light Crude Oil. The key parameters at the operating temperature of 40 degrees Celsius are density of 850 kg per cubic meter, giving a specific gravity of 0.85. More importantly, the dynamic viscosity is 7.5 centipoise. While not extremely viscous, it's significant enough to influence friction losses. We also note the vapor pressure, which is 45 kilopascal absolute. This is a critical number, as we will see later when we analyze the net positive suction head available, or NPSH. Here you see a simplified schematic of the system layout. The pump takes suction from a tank that can have a minimum liquid level of 3 meters above grade. The suction line is an 8-inch pipe. The discharge line is a 6-inch pipe that goes to a dissolver vessel located 12 meters above the pump center line. The dissolver operates at a pressure of 3.5 bar. Understanding this physical layout is fundamental. The elevation difference is the pressures at the tank, and the dissolver defines the static head that the pump must overcome. Here are the specific operating conditions we will use for our calculation. The required flow rate is 450 cubic meters per hour, or just under 2,000 US gallons per minute. We have the atmospheric pressure at the suction tank and the higher pressure in the discharge vessel. The pipe lengths and fittings are detailed here. These are the components that will contribute to friction losses in the system. Note that the discharge line is longer and has more fittings, including a control valve and an orifice plate, which will be significant sources to head loss. To determine the required pump head, we apply the engineering Bernoulli Equation. This equation is the fundamental energy balance for our system. The equation balances the pressure energy, kinetic energy, and potential energy at the suction tank surface, point 1, and the dissolver inlet, point 2. The pump head, H sub pump, is the energy we add, and the H sub F is the energy loss due to friction. We assume the velocity at the tank surface is essentially zero, as it is a large tank. Our main goal is to solve this equation for H sub pump, which is the total dynamic head required. To find the friction losses, we first need the velocities in the pipes. We calculate the cross-sectional areas of the 8-inch suction and the 6-inch discharge pipes using their internal diameters. with a known flow rate. We find the suction velocity is 3.87 meter per second, and the discharge velocity is significantly higher at 6.7 meter per second. Velocity is a key driver of friction loss, which is why the discharge line, with its smaller diameter and higher velocity, we have much larger losses. Next, we determine the nature of flow by calculating the Reynolds number. For the suction line, the Reynolds number is nearly 89,000, which is well into the turbulent flow regime. Turbulent flow is characterized by higher friction losses compared to laminar flow. Using the Moody chart, the Colebrook equation, and the roughness factor for commercial steel pipe, we determine the Darcy friction factor. We have a friction factor of 0.019 for the suction line and 0.020 for the discharge line. This value will be used directly in the Darcy-Weisbach equation to calculate the friction head loss. Now let's calculate the losses on the suction side. We use the Darcy-Weisbach equation, but also account for losses from fittings like the gate valve, strainer, and elbows. Each fitting has a K factor, which is a resistance coefficient. The major loss from pipe friction is 1.07 meters, but the minor losses from the strainer and elbow add up significantly. The total suction friction loss is calculated to be 4.62 meters. This is a relatively low number, which is good for pump suction performance. Turning to the discharge side, we see a very different picture. The pipe friction loss alone is 25.24 meters, driven by the longer pipe length and higher velocity. The losses from fittings are also substantial, with 4 elbows and an orifice plate. The orifice plate, which is used for flow measurement, creates a significant pressure drop of 9.15 meters. The total discharge friction loss is a massive 49.60 meters. This is the dominant component of the system's friction losses. Summing up the suction and discharge losses gives us a total friction loss of 54.22 meters. This is the head the pump must provide simply to overcome the resistance of the pipes and fittings to move the fluid. It is a significant part of the total head requirement, almost equal to the static head. Now, we can finally calculate the total dynamic head, or TDH, using the Bernoulli Equation. We have all the pieces: the pressure difference between the dissolver and the tank, converted to head, the elevation difference, and the total friction loss. Plugging in the numbers give us 107.32 meters. This is the total head the pump must generate at our design flow rate of 450 cubic meters per hour. This is the critical target we need to meet with our pump selection. Based on our requirement of 450 cubic meters per hour and 107.32 meters of head, we begin the pump selection process. We choose an API 610 OH2 pump. We select a model CPX 450 that is designed for these conditions. A two-pole motor running at 2,950 RPM is specified. The impeller diameter is 290 millimeters, is the trim that the manufacturer's data suggests will meet our duty point. This is the key data from the pump manufacturer for our selected pump. The table shows the pump's performance across its operating range. The first column shows the flow rate, the second shows the corresponding head, the third is the pump efficiency, And the fourth, and the one we'll watch closely, is the NPSH required, or NPSHR. At our design point of 450 cubic meter per hour, we see the pump provides 107 meters of head as we need. Its efficiency is 82% and its NPSHR is 4.8 meters. This is the promising starting point, but the NPSH margin is where we need to focus next. Here we introduce the concept of the system curve. The system curve is the mathematical expression of Bernoulli Equation. It tells us that the head required is the sum of the static head, which is constant, and the friction head, which increases with the square of the flow rate. We calculate the static head to be 50.81 meters. Then we find coefficient K by taking our total friction at the design flow and dividing it by the flow squared. This equation, H sub system, equals 50.81 plus K multiplied squared Q, allows us to plot the system curve on the pump curve. The intersection of the pump curve and the system curve is the operating point. This visual shows the system curve. It's a helpful way to see how the head requirement changes with flow. At zero flow, the pump must still overcome the static head about 51 meters. At flow increases, the required head rises parabolically due to friction. By overlaying the curve with the pump's performance curve, we can see the pump will operate at our desired point. This is how we confirm that the selected pump is good match for the system. Now we are calculating the net positive suction head available, or NPSHA, is the amount of energy available in the fluid at the pump suction to prevent cavitation. We use the formula NPSHA equal P atmospheric minus P vapor divided by rho G plus ZS minus HF suction. The first term converts the difference between atmospheric pressure and vapor pressure into head. Then we add the static head, 3 meters. Finally, we subtract the suction friction loss, 4.62 meters. The calculation yields an NPSHA of just 5.13 meters. This is a critical result that we must now check against the pump's requirement. This is the most critical finding of our analysis. The pump requires at its best efficiency point 4.8 meters of NPSH or NPSHR. Our available NPSHA is only 5.13 meters. The margin or difference is only 0.33 meters. This is insufficient. Both EPI 610 and the Hydraulic Institute standards require a minimum margin of 1 meter or a ratio of NPSA to NPSHR of at least 1.3. Our ratio is a failing 1.07. With such a low margin, we are at very high risk of cavitation. This is cause noise, vibration, and rapid impeller damage, leading to pump failure. We must take corrective action. To fix this NPSH problem, we have several real-world engineering solutions. We could 1. Raise the tank level, increasing the static suction head. 2. Increase the suction pipe size, reducing friction losses. 3. Reduce the fluid temperature, which would lower the vapor pressure. 4. Install booster pump upstream. 5. Or select a different pump with a lower NPSHR. like a double suction design. The table shows the effect each action would have on NPSHA. We need to choose a solution that is both effective and practical. After evaluating the options, we selected a combination of actions. First, we will raise the minimum tank level by 1.5 meters, from 3.0 meters to 4.5 meters. This is a simple and effective way to add positive suction head. Second, we will upsize the suction line from 8 inch to 10 inch. This is reduce the velocity and importantly the suction of friction loss from 4.62 meters down to 2.52 meters. The result is new safe NPSHA of 8.73 meters. Our margin is now a comfortable 3.93 meters, and our ratio is a safe 1.82. We have successfully eliminated the cavitation risk. With our pump and head confirmed, we calculate the power requirements. The hydraulic power, the power required just to move the fluid, is found to be 111.9 kilowatts. However, the pump is not 100% efficient. Accounting for the 82% efficiency at the BEP, the required shaft power or brake horsepower is 136.5 kilowatts. Finally, to select the motor, we add a 15% service factor to account for any unforeseen demands. This gives us 157 kilowatts. So we select the next standard motor size, 160 kilowatts or 200 horsepower, a TFC Class F insulation. IP55 motor is selected for reliability and safety in the refinery environment. Okay, now we touch on importance of interpreting pump curves for various operating scenarios. We see 4 panels. One shows the impact of throttling a discharge valve, which changes the system curve and moves the operating point. Another shows parallel pump operation of increased flow. This panel illustrates how impeller wear, by reducing the impeller diameter, will affect the pump's performance. Understanding these curves allows operators to diagnose problems and run the system efficiently. For instance, if the pump is running at the point of the far right of its curve, it may be an indication of wear or a change in system conditions. To conclude, let's summarize our findings. We successfully sized a pump for a critical crude oil transfer service. The design point is 450 cubic meter per hour at 107.3 meters of head. We selected an EPI 610 OH2 pump with a 290 mm impeller, operating at 2,950 RPM. The power analysis showed a shaft power of 136.5 kilowatts and a motor rating of 160 kilowatts. Most importantly, our NPSH analysis identified a critical cavitation risk with the initial design by implementing practical corrective actions, raising the tank level and upsizing the suction line. We increased the NPSHA, achieving a safe margin and a ratio well above industry standard. This diligent process is essential to ensure the reliability and longevity of this critical plant, safeguarding against costly downtime and ensuring the smooth operation of the refinery. Thank you for watching the video until the end. Don't forget to subscribe to the channel and see you very soon.